In this video, we're going to take a closer look at the orbits for the two-body problem when the forces that are involved are inverse squared. It's supposed to be a square here then, obviously, which I forgot. Right. So the force is proportional to 1 over r squared, where r is the distance between the two particles. We've shown previously that with the proper change of variables, you can get a Lagrangian that looks like this. This is just in 2 dimensions. We have r is the distance between the two particles. Phi is the angle that this vector makes with the x-axis. And then we have the potential here, which is corresponding to this potential in this case. This is a single particle Lagrangian, which we've reduced the problem to. We have shown now that phi dot is L over mu r squared. This is a consequence of angular momentum conservation. And we have shown in the last video that under the case where we have inverse square force, the orbits are given by this formula. Where incidentally C is L squared over gamma mu. Okay, so these are the orbits in the case of an inverse squared potential, an inverse squared force. Now what we're going to show is that these orbits, that is r as a function of phi, are all conic sections. So when I say conic section, I mean what you get when you take a cone and bisect it with a plane. So we have this cone, or tip-to-tip cones really, and you cut it with a plane, and depending on how you cut it, the angle of this plane, you can get a circle, an ellipse, a parabola, or a hyperbola. And those are known collectively as conic sections. Okay. Another way to mathematically define conic sections is to say that you have a point here, which we call the focus, F, and then we have a line which we call the directrix, D, and then we're going to pick some arbitrary point here, and we'll take the distance from this point to the directrix, and we'll also take the distance from the focus to this point, and a conic section is given by this focus and this directrix, such that that's the shortest distance from this point to the directrix divided by the distance to this focus is a fixed ratio. So this is how we would put it in words. In other words, the distance from here over the distance there should be a constant. So to see how this would work, we can get the mathematical formula from that. Let's put the focus here at the origin of a coordinate system. So this is x and that's y. It's a little small. Let me blow this up. Now I'm going to call this distance here r, and the distance from the origin to the location of the directrix here I'm going to call p. And I'm going to choose the directrix parallel to the y-axis. And it'll turn out that corresponds to picking a delta here equal to either 0 or pi. Okay. This is going to be the angle phi. That means that this position x here is given by r times cosine of phi, right? So what we're saying is that the ratio of this distance to this distance here, well, this is going to be p minus x, clearly, right? It's supposed to be a constant. So r divided by p minus x equals a constant epsilon. I should also mention that we can actually take the directrix on this side too. Then of course this distance here would be p plus x. So we can either have minus or plus x down here. This should be the formula for a conic section. And like I said before, and as we'll show in a minute, that could be either a circle, ellipse, a parabola, or a hyperbola. Okay, so let's see now if that agrees with what we have up here. Okay, so these are the formulas from this picture. This is what we derived in the last video. And if everything is okay, then this should be the same as that. Well, we can actually see that that's going to work out quite well here, right? If we rewrite this a little bit, we get that r plus epsilon r cosine of phi, and we're going to take delta equal to 0. Equals c. Well, r cosine phi, that's x. That, in fact, we already defined it that way. So we get that r equals c minus epsilon x, or if you will, epsilon times c minus epsilon minus x. Therefore, r divided by c over epsilon minus x should be equal to epsilon. And that's the same formula that we have over here. Just take p equal to c over epsilon. And we can even see that, in fact, if we add in a delta that's equal to pi here, and that changes the sign of this cosine, so it becomes negative. Move it over on the other side, it becomes positive. So we get a positive sign here. So it's either plus or minus. Okay. It's nice to have different colors here. You can indicate plus and minus at the same time with different colors. Okay, so we can see that that's identical to this. Now, let's prove that this type of formula actually describes one of the conic sections. Okay. So we start from here, we get, and then we can square this expression. Now, r squared is the same as x squared plus y squared, right? And we'll move things over a little bit here so that we have a constant on one side of the equality sign and the x and y terms on the other. So that's the equation. In fact, let's make that substitution. So then really you get x squared plus y squared equals c squared. So that's a circle. Which of course is one of the conical sections. Next, we're going to look at 0 is less than epsilon, which is less than 1. So what does that do? Well, if you look here, that means that 1 minus epsilon squared is positive. So that means that the x squared and the y squared terms have the same sign. So we can do then with this equation is that we can complete the square here with the x's. We'll get some constant that will move over on the right hand side. And if we do a little bit of work, we will find then that we get x plus d squared divided by a squared plus y squared divided by b squared equals 1. This is the equation for an ellipse. In fact, this is the equation for a translated ellipse. One of its focuses is, one of its foci is located at the origin, so we can't have the middle of the ellipse at the origin. We will show in the homework what these constants are. That's what you're going to show in the homework. Okay, now we have the third case, which is epsilon equal to 1. That means that this term, the x squared term, disappears. And what we're left with then is just these two things, which we're going to rewrite in this form. And this, it turns out, is the equation for a parabola. Just like this is the equation for a circle, and this is the equation for an ellipse. All right, now there's only one case left, and that's the case of epsilon greater than 1. That's very similar to case number 2 here, except that now epsilon squared minus epsilon squared is negative, so the y squared term and the x squared terms have opposite signs. And that manifests in a minus sign here. We'll do the same thing that we did here. We'll complete the square and the x. But now we'll have to change the signs over here on the y. I'm not going to show that in detail, but you can prove that yourself if you are interested. And this you should recognize as the equation for a hyperbola. And for some reason I capitalized translate ellipse and hyperbola, but not parabola or circle. But these are the 4 results that we get, 4 different equations. And these are the 4 conic sections, which is what we wanted to show here, right? In this case. So what have we shown here? We have shown that when you have a two-body problem with central forces, and the force has an inverse square dependence on the distance between the particles, as is the case, for instance, in planetary motion, then the orbits described by the moving bodies are conic sections. And in the context of planetary motion, this is in fact known as Kepler's first law. Of course, the result to be found is in terms of the relative position r, right? This is r. This is the distance between the two moving objects. In the case of planetary motion, though, one of these is the sun, and it's going to be almost stationary compared to the moving planet. And that's because the sun is so heavy that the center of mass is inside it, almost all the way to the center of the sun in most cases. Okay, so we have proven Kepler's first law. We proved Kepler's second law much earlier in the course. In the next video, we're going to prove the third law, Kepler's third law, as well as one other leftover results that we haven't gotten to yet.